Today we're going to discuss the difference between ionic and metallic bonds. You're also going to discover how to draw ionic bonds. First, let's define bonds. Bonds are things that hold atoms together, and they either make larger compounds or molecules. Typically, when a bond forms, there is a loss of energy because the molecule or compound that's formed has greater stability. Now let's talk about one of the bond types. Ionic bonds, you can sort of get a clue from the name. It's because there are two ions or two charged particles that are attracted to each other. So we say it has an electrostatic charge. Note that there aren't actually any physical connections between the two charged particles. They're attracted to each other because of their opposing charges. They're not actually physically connected, so there's no physical connection. So let's reach back and we're going to talk about Lewis dot diagrams first. In a Lewis dot diagram, if you recall, the element symbol, and we're going to start with Na and Cl, the element symbol, which we call the kernel, represents everything in the atom that is not a valence electron. And then in order to determine the dot structure around that, you would look up the valence number. Sodium, when you look in the periodic table underneath the symbol, you're going to see the last number in the electron configuration is 1, so it would get a single dot. Chlorine has a valence number of 7, so the kernel represents everything else in the atom, the protons, the neutrons, all non-valence electrons, and then we're going to put 7 electrons on the outside. I'm going to use X's for the dots on chlorine. You don't have to do that, but it's going to show you what happens in an ionic bond, so I encourage you to do this. If you recall, when we put our dots, the first 2 go on top to represent the S sublevel, and then we put 1 on each side to represent the 3 P's before we go back and add in the rest. So with this illustration, you can see sodium has just 1 valence electron, and chlorine has 7 around it. Chlorine would really like to have 8 valence electrons, and sodium would like to lose it. Remember, metals are losers, and nonmetals prefer to gain. So the relationship between these two atoms would actually be better if sodium were to lose its electron to chlorine, and that's exactly what's going to happen. And I'm going to draw this below so you can maybe see a little better. What will happen when sodium loses its 1 valence electron, it'll become a positive ion. And if you recall from when we did this earlier in the year, you always put brackets and then the charge if there's a loss or gain of electrons. Chlorine, when it picks up that extra valence electron from the sodium atom, it will look like this, and this is why I used X's versus dots so you could see where it came from, will then become a negatively charged ion, and if you wanted to put in the value of the charges, you could. And now that actually represents the ionic bond because the two are attracted to each other because of their opposing charges. For the next example, I'm going to bring in the periodic table because it may not be really obvious, the valence number, because these are elements we don't use quite as often. In order to figure out the valence number, I just want to show you again. For gallium, here's gallium here. It has, in its electron configuration, if you look way down here, it has a number 3. And then bromine, you'll see right here, has a 7. So if you weren't following before, hopefully you see that now. So gallium, when we first draw it, would have 1, 2, 3 valence electrons, and bromine would have 1, 2, 3, 4, 5, 6, 7, much like chlorine, since they're in the same chemical family. So here there's maybe a little trickiness going on because gallium isn't going to lose just one valence electron, it's going to lose all 3. But bromine only has room for one more electron. So how is gallium going to be satisfied as well as bromine? And the only way to do this is actually to have more than one bromine. In order to find a home for all 3 of these electrons, you're going to need to have 3 bromine atoms. So here's what we're going to do. We're going to show gallium now without its valence electrons. So it will end up with a +3 charge. And then each of our bromines will end up with 1 of galliums. So we're going to need 3 bromines here. It'll be a -1. 1, 2, 3, 4, 5, 6, 7, and the 8th comes from gallium, so I'm drawing it as a dot. Again, you don't have to do that, but it does help to show you what's happening. 1, 2, 3, 4, oops, I'm doing them out of order. Don't tell. And then -1, like so. And that's how you would show gallium and bromine forming bonds together. All right, a couple of things to note. Whenever an ionic bond happens, it's because a metal and a nonmetal have formed bonds together. One losing electrons, the metal, and the nonmetal gaining those electrons. As a result, we say that ionic bonds are characterized by a transfer of electrons. Anything that's ionically bonded, we call a salt. So NaCl is not the only salt out there. That gallium bromide that we just created is also a salt. Anything that has a metal bonded to a nonmetal or is ionically bonded is a salt. All right, moving down on our paper here, we need to discuss what the bond tells you about the different properties of the substance. The stronger the bond is, the higher the boiling point is going to be, and the harder the substance will be. If you recall from earth science, halite was one of the rocks that you guys studied, and halite is actually sodium chloride. It was a very hard rock because the bond is actually relatively strong. And in order to figure out the strength, we actually determine that by calculating the electronegativity difference. Or, because we're super lazy, we abbreviate this END, or electronegativity difference. So the greater that difference is, the stronger the bond is. So the higher the END, the stronger the bond. All right, next page we're going to talk bonds. In metals, they're actually held together by metallic bonds. Held together by metallic bonds. So whether you have an alloy, a mixture of metals, or if you have just, pure metal, those atoms are actually held together by what we call metallic bonds. Metallic bonds are characterized as a sea of electrons. And the reason we say that is that those electrons are not owned by any one atom. They can move around. And in this little diagram you have here, they're represented by the little green dots. And they're just sort of floating around in there, which is why electricity can happen. Those electrons can flow through this metal, which is electricity. Now, I mentioned alloys, and alloys are something you covered a long time ago in lab, but they are a mixture of 2 or more metals. What's interesting about alloys are, as soon as you melt the two metals together, they become homogeneous, which is pretty impressive because most things don't do that for us, but metals do that. Examples, pewter. If you've ever picked up a silver-colored figurine and thought, geez, that's heavier than I thought it was going to be, it's because it's probably pewter, which has a lot of lead, which is a very dense metal. It also has tin, and it has copper in it. Brass, which you guys made in lab when you did the alchemy lab, is a mixture of copper and zinc. If you recall, you kind of plated the zinc on the outside of the penny, and then when you melted the penny a little bit, the copper and the zinc blended together homogeneously, forming brass. Another example is steel. Steel is actually iron and carbon and a couple of other trace metals. Carbon's not actually a metal, but that's what gives it its strength. And then another one you've probably talked about in history class is bronze. Bronze is a mixture of copper and tin. Also a really awesome tool making metal. So let's look at some different ionic compounds, and what we're going to do is we're going to look up their electronegativities, figure out the difference, and then once we've figured out all of the electronegativity differences, we can rank them based on those with the strongest bonds. So we're going to need, in order to look up electronegativity, we're going to need our table S. So here's table S, at least the first page of table S, and we're looking for sodium. Sodium is number 11, which is right here, and you can see its electronegativity is 0.9. So I'm just going to record that right here. And then we need to find chlorine. Chlorine is number 17. Here it is. Here's number 17, chlorine, and its electronegativity is 3.2. So in order to find the difference, we just need to subtract. And when we do, we get a difference of 2.3. We can't do the ranking until we've done all the electronegativity differences. So I'm going to do one more with you, and then my suggestion would be to pause it and then try them all yourself so that you know what you're doing. So the next one we're looking for copper, and copper is number 29. It might be easier for you if you have your periodic table out as well to find it, but its electronegativity is 1.9, and then chlorine we had just looked up is 3.2, and now we find the difference, 3.2 minus 1.9, and we get 1.3. At this point I would pause it and try it yourselves. All right, so now that we have all of our electronegativity differences calculated, we can do our rank. Remember that the greater the difference, the stronger the bond. So the greatest difference is with barium fluoride, so that's going to be number 1. And then the next greatest difference is with the potassium chloride, which is number 2 then. Here we have number 3, 4, 5, and 6. And that's all there is to it. When you compare two ionic substances, all you're going to look at is the electronegativity difference. Also, this would rank your boiling points. The barium fluoride would have the greatest or highest boiling point, and the copper chloride would have the lowest boiling point. All right, now we're going to practice drawing some salts. My suggestion whenever you do this is first draw the dot diagram. Recall that you're going to need to look up on the periodic table what the valence number is. Calcium is 2, and then iodine is 7. So in order to find a home for each of the electrons from chlorine, since iodine can only hold one more, you're going to need 2 iodines. So you'll end up with calcium with a +2 charge, and then you're going to need 2 iodines in order to find places for each of the electrons from calcium. I'm going to show you a little trick right now, since we've now done the ones in the notes. Instead of drawing 2 iodines, which is perfectly acceptable, you can actually just put a 2 here, indicating that you would have needed 2 of them. Feel free, though, if you want to continue to draw 2 of them, to do that. All right, then for magnesium and phosphorus, magnesium has a valence number of 2. Phosphorus has a valence number of 5. So this one's a little trickier. we're going to actually need multiples of each of those. And you can kind of do this like we figured out the formulas. So if you look up oxidation numbers, magnesium would be +2, and then phosphorus would be -3. It wants to gain 3 electrons, so it's full. 1, 2, 3. So all you do then is swap and drop. Or you could actually figure it out based on how to find homes for all of the electrons. So we have magnesium now losing both electrons, so it ends up being a +2. And then if phosphorus is going to gain 3 electrons, the least common multiple of the +2 and the -3 is 6, meaning that you're going to need to have 6 electrons exchanged. So the only way to do that is since magnesium only has 2 to give, if you have 3 magnesiums. And the only way to find homes for all 6 of those electrons with phosphorus is to have 2 phosphoruses, if that's a word. So I'm going to use subscripts to show this, but you are certainly welcome to draw out 3 magnesiums and 2 phosphoruses. And that's how you do ionic bonding.